In section 6 of chapter 9, we're going to now start algebraically approaching these exponential functions, but we're going to approach them from a different perspective. In the past, we focused on graphing, shifting it left or right, up or down, stretch or press, all that. Now we're just taking a pure algebraic approach, which is utilizing exponential functions to actually solve or compute something. Today, in this lesson, we are going to be talking about compound growth. First, I want to show you a basic way that you can invest money that you should never ever invest money in, which is utilizing something called simple interest. Let's imagine you had $10,000 and you were going to invest it. And the first option is to invest in what is called simple compound interest. What simple interest means is it's going to take the amount that you invest, and at whatever given rate it is, for this one it's 8%, that's how much it's going to increase by every single year. So for example, if you have 10 grand, you're investing it at simple interest rate at 8%. 8% of $10,000 is $800. That means at the end of every single year, that account is going to grow by $800 every single year. So at the end of the first year, they're going to throw in another $800 into your account. End of the second year, another $800. Third year, another $800. If you model that over a 50-year track, that $10,000 will balloon into $50,000. This is a horrible investment plan because, as you might be able to see, this is a linear growth pattern. It is a straight line. You can have a better investment opportunity if you use something that is called compound interest. Compound interest models exponential functions. Instead of saying, oh, it's going to grow at 8% simple interest, just adding $800 every single year, what it does is it says, I'm going to analyze what's in the account at the end of the year, and I'm going to take 8% of that and add it to the account. So at the end of the first year, it's still going to add $800. But then you'll have $10,800 in your account. End of the second year, they take 8% of that $10,800, and so you're going to get a little bit more. So if we were to make that investment plan, you start with $10,000. If you wait 10 years in this same plan, it's just simple interest versus compound interest. The compound interest, instead of being $18,000, will become $21,000. An extra $3 grand. If you're into gaming like me, it's an amazing gaming PC. Not bad. But if you decide to hold off, you're like, no, I think I could wait 20 years. You'll have $46,000. That's an extra 20 grand. That's like a decent-ish car. That's like a cheapy Toyota Corolla. But let's say nah, I want to plan for my retirement. You just put 10 grand in, you're going to work for 30 years, and then you're not going to touch that 10 grand in this account. You're just going to wait for 30 years and see what happens. Instead of $34,000, it's worth $100,000. That's a much better car. That's a pretty souped-out Tesla. But let's say, no, I really love your career. You're really passionate about it. You're going to stay in that career for 40 years. So you're going to leave this $10,000 in your account for 40 years and not touch it. $2 grand, you now have $217,000. Exponential functions grow ridiculously quickly. This is how retirement plans operate. They grow in this style, in this pattern. If you left this alone for 50 years, it's almost $500,000. Starting at 10 grand, did nothing to it, grew to $500,000. I'm going to show you the equation so that you can model this. So if you want to start planning for your financial retirement, you can start doing that this afternoon if you wanted to. Here's the formula. I will forewarn you, this formula shows up in a bunch of different subjects. It shows up in math, it shows up in biology, shows up in chemistry, probably shows up in physics, but I can't think of a way or where it would. It shows up in business all the dang time. Each subject, annoyingly, changes the letter of the variable. The format will still be the same, but for example, in mathematics, the C we use for C, but in business, they use a P instead of a C. They just use a different letter, but it's still the same math. Y is going to represent the final amount. That's how much money you're going to end up with at the end of your investment. C is going to model how much you're going to start with. It's your initial amount. They use P in business because P stands for principal. Then you're going to have a K value. K is going to represent the percentage rate of growth or decay, because it can model both. If your percentage growth is positive, you're going to write your percentage as a positive decimal. So my example, if you have a 23% growth, you're going to plug in 0.23. If you have decay, you're going to plug it in as a negative number. So 7% decay would be negative 0.07. And then lastly, T is going to represent how long you're going to leave it alone. T is time. And N is how often it is going to compound. That is to say how often it's going to grow in value. In the problems I'm going to provide, I'm going to tell you all the information that you need. This is basically a word problem, but I just pulled out the pieces that matter, and I put them in order so you don't have to parse through what part means what. Because these are very computationally heavy problems, I am just going to grade you on what you have written for the function. I am not going to grade you on what you calculate the value to be, because it is very easy to type this into a calculator incorrectly. Specifically, it's difficult if you have a non-graphing calculator. It's hard to type these incorrectly, and it's also very difficult to understand when you get it wrong. If you type it on Desmos, it will pop out fairly nicely. So problem number 1, I have an initial amount of $500, an annual rate of growth of 13%. It's compounded monthly, and the time is 13 years. Here's how I'm going to go about doing this. It's going to be y is equal to my initial amount. I initially started with $500. I'm going to multiply that by 1 plus, it is a growth rate, so that 13%, I'm going to write as a positive value, 0.13. Oops, don't need to press it yet. That's going to be divided by, and now here's where things can get tricky. I need to ask myself, since it's compounded monthly, that is how frequently the amount of the balance is going to increase. It's going to increase at the end of every month. I have to ask myself, how many months are there in a year? Annual means year. Well, there are going to be 12 months in a year, so I'm going to divide this by 12. And that'll be raised to the power of 12 times. And then I need to ask myself, if the rate is annual, how many years are there in 13 years? Now that's a relatively easy question. That is that there are 13 years. So I'm going to put a 13 right there. And this is what I'm going to be assessing you on, is can you set up the equation properly? Because we don't have access to graphing calculators, I'm not going to require that you get the answer to this, although I'd still recommend that you try so you can practice inputting these values into calculators. Now problem 1 is not that difficult because the units relatively line up smoothly. Problem 2, not so much. Problem 2, I have an initial amount of 1 million cells. There's an hourly rate of decay at 7.3%. It's compounded every single minute, and the time I'm going to let it do its thing is for 2 days. So this is going to be y equals my initial amount, which is 1 million, times the quantity of 1 plus my percentage decay, which is negative 0.073. And that's going to be divided by, now I'm going to divide it by the rate, or sorry, how many times it's going to compound. I have to ask myself, how many minutes are there in an hour? Well, there are going to be 60 minutes an hour, so I'm going to divide it by 60, and that'll be raised to the power of 60 times, and I'm going to let it run for 2 days. I need my units to match up. So 2 days, I have to ask myself, how many hours are there going to be in 2 days? The answer is 48, so I bring it to the 48th power. Now the reason that we are doing that, the reason we aren't just plugging in a 2 there, is we need the rate, the number of times we compound, and the time to all be in the same units. It is easier to change minutes into hours and to turn days into hours than it is to manipulate these hours. Because if you change the hours, that changes the percentage. Changing these two just makes us have to manipulate one value. Changing the percentage, you're going to have to do another computation, so we generally say don't change the percentage rate of growth or decay unless you absolutely have to. Problem number 3, same thing. Initial amount is $7,500. We have a monthly rate of growth at 0.9%. It's compounded daily, and the time we're going to leave it alone to do its thing is a decade. So as an equation, this is going to turn into y equals 7,500 times the quantity of 1 plus it's a rate of growth, so it's going to be positive, 0.009, divided by, and now we need to find out how often it's compounding. It's compounding daily. How many days are there in a month? Yes, it changes from month to month. In mathematics, we just round it to be about 30. And that'll be brought to the power of 30 times the amount of time I'm going to leave it be. I'm leaving it alone for a decade. I need to figure out how many months are there in a decade. There are going to be 12 months per year. So 10 years in a decade, 12 times 10 is 120. And this is my function.